Yeah, first of all, thank you for waiting for my talk, because the day is the last day and it is a long day. So, I am Dr. Sucheta Mundal and I am assistant professor in Shibnadar Institution of Eminence, which is situated in Dadri, which is far from even Noida and Greater Noida. I am there for last 3 years, and I have my group. They are working on spintronics, which is an emerging field which combines the efficiency of electronics with the beauty of spins into it. So, I will be talking about some projects which I actually pursued during my doctoral and postdoctoral studies. But before going into that, I will definitely show you how we are doing in SNU. So, this is our beautiful campus, and Mr. Shiv Nadar from HCL, the founder of HCL, he actually created this philanthropic university, and many of you actually know about this, whoever is not aware of this. So, that is why I just projected this slide. So, these are the some initial days when I tried to set up my laboratory. The first instrument that I procured there and custom built is a ferromagnetic resonance technique, which can actually probe electrically spin wave dynamics in gigahertz frequency scale, and many of you have already shown nice results out of it, but we are a new group, so we are in the developmental phase. So, our FMR also is going through upgradation to STFMR later part of time. Recently, with collaboration between our PhD physics and chemistry department, we have also procured ultra-fast laser. So, the plan is to initially measure the transient absorption spectra for some of the optically active materials, but then we will convert that setup into time resolved MOC. So, I will talk about time resolved MOC in my talk a lot, because that is what we used for measuring the spin dynamics. There are also other facilities in our institute which is central, for example, sputtering, AFM, XRD, PPMS and many other facilities which really help us in doing some in-house study and not really relying a lot on collaboration, but also we are open to collaboration and we are collaborating with NPL, we are collaborating with some other institutes like SN Bose for pursuing some difficult measurement which is not, and sensitive measurement which is not possible within the institute. So, the first set of work which I will present today was done when I was a PhD student of Professor Anjan Bormon. Many of you might know him. He is from SN Bose and he will also move to Shiv Nadar University in some recent time. We studied all optical detection of spin current in various manner. For example, in heavy metal ferromagnet interface, we sent charge current and then we excite the spin dynamics to the adjacent ferromagnetic layer, and then we could probe the spin dynamics, and from there we can passively detect the spin current conversion efficiency. We also have studied the effect of heat in those devices, and we have also studied, and this is the first report, which is all optical detection of interface spin transparency, particularly spin pumping in beta tantalum and coffee bee interface. Later part of time I moved to Berkeley for my postdoc with Professor Jeffrey Bocker, and there I got an opportunity to combine my work with 2D material. So, we studied ferrimagnet and graphene interface. There we optically generated spin current at the interface, and not only the precisional dynamics, I will explain what is that, also the ultra-fast demagnetization and remagnetisation got affected by the hybridization between two interfaces. So, this is the setup. One is based on the oscillator laser. This is called time resolved magneto-optical Carr effect magnetometry, in short TR-MOC. We probe the magnetization, the time varying magnetization from let us say femto to pico to nanoscale nanosecond time scale. So, this is a tri-sapphire laser based cavity, oscillator cavity, which can emit fundamental of around 800 nanometer. Then that fundamental is split into two. One part is being frequency doubled, which is appearing as the violet light. Another is the probe, which is time delayed with this delay stage, and then the time difference between the pump and probe is kind of varied to get a time dependent signal. So, what we can study I will explain in the next slide, but before moving forward, we also had in SNBOS, which is I was involved in the development of this laboratory, and that is a amplified laser. So, amplified femtosecond laser is a very powerful laser, and the repetition rate was also much low, about a kilohertz. So, the pulse energy is very high, the pulse width is about 30 to 40 femtosecond. So, we could probe nicely ultrafast demagnetization with really good resolution. So, this setup help us in studying many fluence dependent study, also wavelength dependent study, because this setup comes with an OPA, optical parametric amplifier, as well with it. So, many of the laser parameter which might be useful for the audience is listed here. Here is a summary of how we obtain precision or ultrafast demagnetization. So, let us say a collinear geometry is projected here, where the pump is hitting the sample and then exciting the dynamics. The probe pulse is approaching normally, and we are obtaining polar Moog signal in this geometry by saturating our magnetic sample, but giving it a slight tilt to induce precision later part of time, which is a trick that we apply in the system. So, what happens when femtosecond pulse is approaching the ferromagnetic material? So, the spins are aligned and the pump pulse is hitting the sample in presence of a magnetic field or without it, the thermalization anyway will take place. Okay. So, the ultrafast demagnetization is the first phenomena that we should observe within few hundreds of femtosecond for most of the material that vary. Then a remagnetization takes place. The remagnetization between 3 degrees of freedom, one is spin degrees of freedom, electron degrees of freedom, and lattice. So, remagnetization happens in 2 steps, one is called the fast remag, another is the slow remagnetization. If there is another external magnetic field present or internal magnetic field which is in form of anisotropy field present in the sample, the spins will relax as well as they will be experiencing a torque which will make them precise. This precision has 2 components, one is frequency, another is damping. So, damping is of course it is there obvious. So, damping will be also calculated from the envelope of the dying signal which we get in the time resolved spectra. So, the typical timeline of this phenomena is, like I mentioned, from femtosecond to nanosecond. We have combined also spin current into it. I mean, we are studying spin dynamics in ferromagnets, but we also are generating spin current in another layer, like you have already seen many of the in many of the talks. So, there are various types of spin current. What I mean by pure spin current is when you apply a charge current, let us say, or you might not apply, I will explain that when I will be explaining spin pumping. In that case, what happens that the up and down spin with opposite polarity will get deflected into opposite direction. So, that will create a spin imbalance. So, without any charge imbalance, if there is a spin imbalance, that is called the pure spin current. And spin Hall effect, also spin pumping effect is examples of such spin current. So, our group studied this in 2014 where A. Ganguly et al. And lots of other people are involved. So, they studied in platinum and permalloy bilayer how this time domain detection can be helpful for detecting the modulation of damping, and from there we can actually calculate what is the spin Hall angle of a material. So, later part of time this experiment was tried with different materials, and I will present 2 material, one is tungsten, another is tantalum. So, what originally happens here, I tried, this is a humble try to represent the phenomena, it might not be exactly accurate plus but please bear with me. So, there is 2 layer, ferromagnetic layer and heavy metal layer. Once you apply charge current, the spins with opposite polarity will get deflected into opposite direction. So, naturally there will be generation of spin current at the interface, which is presented by this brown arrow. Now let us assume that the top layer is having or receiving a pump pulse. So in presence of external magnetic field, the spins will try to precess, okay, and I have made the direction arbitrary because the angle between H and angle between the spin polarization has some role to play. So what happens, there is natural damping and frequency like I mentioned. In addition to that, in presence of spin current, there could be damping like torque, and damping like torque can reduce damping or enhance damping depending on in which direction the spin current is acting. So if you change the charge current polarity in case of spin Hall effect, the spin current polarity also will get reversed. So similarly, the damping will be also decreased or increased. Field like torque is also there, but in some cases they are negligible, so I will talk about that later. The probe pulse will now detect the dynamics and will help me passively detecting the efficiency of the heavy metal layer. This is modified Landau-Lipschitz-Gilbert equation, where the first term is corresponding to precision, second term is damping, third term is spin transfer torque term, and the last term is field like torque. So by cultivating a little bit this spin transfer torque term, modulation of damping can be represented with these parameters and experimentally can be found. After we found modulation of damping, which is delta alpha by Jc, Jc is the density of the charge current, delta alpha is the change of damping of the adjacent ferromagnetic layer, then we can actually get the spin Hall angle from this formula. So in the first paper, which was my first paper in 2017, we studied tungsten, and we of course have observed and phase transition. So tungsten is known to exhibit phase transition in various conditions. There could be oxygen doping, there could be other changes. We have varied the thickness of the tungsten, and due to some chamber condition, we have achieved this phase transition from beta phase to alpha phase, which is from A15 to BCC in this thickness range. So we have verified those by characterizing them in electrical technique and also from X-ray diffraction, how is the phase, and then we have performed the optical experiment. So here is this is the background subtracted precisional data fitted with the sine formula, and a plane sine theta envelope you are seeing, plane sine theta variation you are seeing with the envelope of exponential, and that envelope will give us idea about damping, right. So these are plotted with changing Jc, which is the charge current density. So for one polarity, which is positive polarity, we will see that the damping is high. However, for the negative polarity of the charge current, the damping is improved or the profile is improved. So we have now plotted those numbers and they are falling in the linear trend. So this trend is giving us the amount of mod, which is modulation of damping. So after getting mod, we have used the previously described formula to extract out a spin Hall angle. So now we have plotted our spin Hall angle for different tungsten thickness, and we have this non-monotonic change. Now beta tungsten is having higher spin orbit coupling, that you know, but why even there is a drop at this moment, at this thickness. So the drop simply means an underestimation of spin Hall angle for that particular thickness, because when we have two layers coupled, there is also another important term that you have to keep in mind is spin diffusion length. So spin diffusion length for tungsten falls in the regime of 2 to 3 nanometer. So this regime is suffering from backflow, that is why there is an underestimation. The highest spin torque efficiency or spin Hall angle we have obtained in this system is about 40%, which means 40% of the charge current can be converted into spin current, which was moderately high of if we compare publication in that time. We also have varied shown the change in frequency, but this frequency modulation is symmetric in both sides with the charge current polarity. This indicates to slight Joule heating or heating effect in the devices. So later part of time I will just briefly touch this, that using a beta tantalum coffee bean system, we also segregated the amount of real change from charge current and the effect of heating, how we can segregate. So we have tried this in a system where there is no complicated phase transition. So, this is a beta tantalum which is deposited from 4 nanometer to about 20 nanometer, and then the surface roughness is quite smooth, which also is reflecting the interface might be smoother. Then we have performed the same type of modulation of damping experiment, and we have characterized that we have found the frequency modulation is again symmetric for both sides, and then we have fitted them using this formula. And after fitting this asymmetric background, we actually got two different numbers for damping like torque efficiency. So, the number with heating effect is slightly high, which is around 60%, 0.6, however around 0.4, however for the number without heating is around 4, but it is 0.4, but it is slightly less. So, the point that we want to make from this study, that if we can segregate out the effect of heating from our devices nicely, we can actually match the results, and whatever is the actual efficiency of the underlayer, we can report it. Okay, so the next is about the spin pumping effect, which is all optical spin pumping effect. In that case, what happens? We do not really apply any charge current in this layer. What we are doing, we are simply exciting spin wave dynamics in this top layer by pump probe method, and then the spin which is precessing is transferring angular momentum to the adjacent tantalum layer. And because of this transfer of angular momentum or transfer of spin, there is a transfer of spins which is also diffusing with according to the diffusion length of the material. There could be also backflow depending on the thickness of the layers. So, this phenomena is studied varying both coffee bean layer thickness and tantalum layer thickness to verify certain parameters. What are those interesting parameters? Like in the previous talk also, we have came across a question that what is the role of interface, whether it is transparent and it is allowing the spins to flow easily to the other layer or being detected easily. So, the role of interface is very important in this case, because interfacial transparency term is there, and this is called effective spin mixing conductance, which is a measure of how good the interface quality is between the tantalum and coffee bean. And for us, the reported spin transparency is about 50%, which means this beta tantalum and coffee bean interface which we have formed is allowing the total amount of spin current is 100% and allowing 50% of that to be transferred. If you can improve this interfacial parameters, then actually you will get you will apply less energy to the system and will get more output simply. The last the last part of the talk which I would like to touch is when we performed optical experiment on graphene and cobalt gadolinium system, what we observed. So, we tried regular exfoliation method which is cheap and effective. There are also many studies have been done in Professor Muduli's group, also in Professor Baumann's group before. So, this comes after that, and what we tried is we tried to exfoliate different layers of graphene. So, we kept constant the ferrimagnetic layer thickness and we varied the graphene layer thickness, and fortunately, so fortunately we could achieve from monolayer to bilayer to tri-layer to few layer and graphite. So, we have characterized these properties including how the defect is evolving from Raman mapping as well, and also we have calculated the defect density. We have basically characterized how good or bad our films are. So, when we did not sputter another ferrimagnetic layer on top of graphite, in that case actually what happens that the defect peak arises. So, we feel like our exfoliated graphene was clean and atomically also more or less there was no defect, but when we bombarded with ferrimagnetic ions or it was co-sputtering cobalt and gadolinium separately, so in that case defect appears. So, these are the time resolved data. The left panel consists of negative delay, then ultra fast demagnetization, fast and slow demagnetization. and the right hand side panel contains the precisional term. So, you see that this is the normal cobalt gadolinium signal that I am supposed to get, and then when there is monolayer graphene attached to it, it is so fast. I mean, it is probably half of the demagnetization time that we are getting. So, the dynamics is accelerated. Later part of time we also observe that the damping is more for monolayer, and also there are some other samples which is giving us such non-monotonic change. So, without taking a look at the spectra itself, let us see what is the parameter variation. Yes, so I will be done soon, I hope. So, this is the effective damping which is non-monotonically varying. Our assumption or our interpretation is that monolayer graphene is weakly spin orbit coupled, but when it is adjacent to another substrate, there are substrate induced effects and layer induced effects which is enhancing the intrinsic SOC. So, this is the extrinsic SOC which is increasing the damping. Similarly, for demagnetization time also, the enhancement of SOC might be introducing spin flip scattering in the system, and that is why demagnetization time and damping had an inverse relationship for most of the samples. Slow demagnetization time is getting affected non-monotonically, and for graphite it is very high, because graphite is not allowing to pass the deposited heat from the probed region to the substrate easily to the lattice. So, it is restricting, and that is why the lifetime is increasing. The fast demagnetization time is decreasing because there are not only electron-electron scattering, but there are phonon mediated scattering or acoustic phonon mediated scattering, which is causing such changes in the sample. So, because of in the view of time, I will just be a little quick on this slide. If you have any question, please feel free to ask. The summary is that we have detected spin Hall angle in an optical method for tungsten. We also have segregated heating effect in tantalum and coffee bean system, which can be modeled for other systems as well. There is a first ever observation of all optical spin pumping effect in tantalum coffee bean, which we published in Science Advances that time. Accelerated ultrafast dynamics has been reported in hybridized interface, which is graphene and ferromagnet. So, graphene and ferromagnet is very different from heavy metal and ferromagnet, because the changes in graphene not only is behaving based on just spin orbit coupling, there are also other hybridization involved. There are also, let us say, their thermalization properties are involved. So, there are lots of things which graphene can do on the sample. Okay. So, now little bit fun part of the slide, which is I am going to promote two conferences which we are organizing in this year. One is this year September, another is next year. I would just request to take a picture of those slides and circulate among your groups if you find someone interested to apply, and yourself as well. So, you are you are cordially invited. So, one is invitation to the symposium on women in physics, networking, innovation, opportunity and equity. So, which is being held on 11th and 12th of September. If you are interested or some of your colleague might be, please feel free to share this slide with them, and let them approach us. So, I will be convener with fortunately Poonam Mehta, which you know by now. And there is another program which is very specific to this Indian subcontinent, because this is the first time a translational roundtable on magnonics is going to happen in India. So far it has been happening in Poland and other part of Europe. So, we are fortunate that we are bringing this event and the global event in Shiv Nadar University. So, in partnership with Ashoka University, IIT Delhi, Professor Muduli is here, IIT Mandi, Professor Aarti Kashyap is there. Also, you may write to Professor Anjan Barman and Professor Anil Prabhakar, who are the chairs of this event. So, with that I would like to just thank you for listening.
Thank you, Sujita, for your nice talk. So I have two small questions. Like, first is why graphene, and second is like, so you create a kind of defect in graphene. So is it due to your materials or due to the spot rate? They have a very high energy and they create defect. So can you just
Yeah. So graphene is a very interesting material. It has been studied in spin transport type of experiments for long. It also reported that graphene itself can have magnetization. It is also reported graphene can have proximity induced magnetization. So graphene has a lot of thing to offer. Now our try was what will happen if we don't just work with graphene, but we keep adding layers to it, making it layer dependent. So what will be the layer dependent changes in graphene that will affect the dynamics of the adjacent layer. So that was one try, and the answer to your next question is yeah. Yeah. So the answer to your next question is the defect we didn't intend to create, but after it was created, our interpretation is if you bombard a clean graphene surface, particularly monolayer graphene, with sputtering, and the sputtering power is considerably high, you are going to eject or knock out some atoms. So they are there, and that is why graphite is less affected, but graphene is more affected by this bombardment.
Hello ma'am, thank you for the call. My question is that what is the role of the thickness of the spin current source if we want to know the exact role of the spin Hall effect in the generation of the spin current? At which extent, if we vary the thickness, then the spin current source, spin current generation will be got saturated.
Okay, that is a very good question. So I will quickly switch to one slide, which is probably this. If you are interested in varying the non-magnetic layer thickness, then pay attention to the second graph, which is showing delta alpha versus T, right? And T is the thickness of heavy metal. Now this is a non-monotonic increase, but then it is saturating, right? So there will be saturation for most of the material after spin diffusion length. So if you know the spin diffusion length of your material already from literature, then it is better that you work in the regime where it is above the spin diffusion length, so that you get the maximum detectable damping or detectable change. That is what is there. But if you discuss about the original thickness dependent of spin Hall efficiency or spin current efficiency, in that case you also have to think about other effects like Rashba effect. So if you are making your samples too thin, you might also experience Rashba effect, and that might have a better degree than the bulk spin Hall effect in some cases. So there are materials which actually can be tested from atomically thin material to maybe 10 nanometer thickness, where most of the phenomena will give you different weightage and different benefit. So
means in all cases the interface effect, because spin current generation via the Rashba effect will be the constant. So is there any way to distinguish between the spin Hall effect generation or due to the Rashba Hall effect?
Yeah. There are theoretical models already. If you follow the group of Dan Ralph from USA or someone like him, they have already written nice review papers on such topics, and they are working on this direction for long. So you might follow some of the papers and then actually find your answer, that how you can segregate Rashba effect and how you can enhance spin Hall effect in some of your materials. Yes.
Thank you.
Speed transparency. In one of your slides, you got something like
Yes.
sphere 50%. How to control and improve it?
Yeah. So when we are talking about spin transparency, we have got a fixed number here, but what we believe, or I have also come to know from some of my colleagues recently, that let us say we are working with something like platinum. Platinum also might have proximity effect. So for them, proximity induced magnetization in platinum is enhancing the spin transparency. Spin transparency depends on, for example, the like I mentioned, spin mixing conductance and chemical potential of the material at the interface. So if we can actually choose materials which will have better chemical potential, how I should say, for example, think about impedance matching of a circuit. If you can find better impedance matched circuit, then your load will be accordingly distributed. So, similarly there are materials which will have better matching at the interface, and there I think interface transparency will be also improved.
Nice talk, ma'am. So I have a very general question that is it possible to probe antiferromagnets by TRO?
Yeah.
So,
So, one of the
because
talk
it
was
has a
about that only, right?
because
Antiferromagnet.
it has a very fast terahertz dynamics. So
Yeah. See, TRMO works between femtosecond to nanosecond. So, picosecond dynamics are already proved in TRMOC also. So, people have seen another effect which is similar to Carr effect, it is known as void effect, magneto-optical void effect. So, that void effect, the mechanism is very much similar, it is working on the change of light's polarization, but if you are working with non-collinear antiferromagnets, the void effect is helping you in sensing the non-collinear spins and their dynamics, similar to TRMOC. So, definitely you can probe spins with TRMOC, antiferromagnetic spins as well. Yeah.
Any other questions? If not, let's thank the speaker once again.
Thank you.